Well, welcome back. Now we're going to start part 2 of lecture 6 in the Introduction to Radar Systems course. But before we move on, it just occurred to me as I was starting this introductory view graph that I mentioned in the introduction to the whole course that I'd be noting throughout the lectures the different people in that list and the acknowledgments, and sort of putting an individual person with their really great helpful contributions to the visuals in each of the lectures. And so what I'd like to do is to just take 30 seconds right now to go over and to not just have a list of names, but put lectures with those names. Dr. Andy Gerber with the introduction view graphs, Dr. Steve Wiener with the radar equation, Dr. Bob Galish in the propagation effects, Dr. Bob Atkins in the target cross-section lectures, Jim Ward in the detection lectures and in the signal processing lecture. I'm fully to blame for the clutter lecture. Dr. Pamela Evans she gets kudos for a lot of great visuals that she developed that I'm using, along with a number of mine in the antenna lecture, and Dr. Kathy Rink in the tracking and parameter estimation, and then Jeff Hurd at transmitters and receivers. So that just quickly puts a name with the contributions of the different people. And as I said before, if there's a problem, blame me. If you really love those visuals, give them the kudos. So now we'll move on to part 2. Polarization is defined by the orientation of the electric field vector as it propagates in time. And going back to early lecture, the simplest electromagnetic wave is one where we have an electromagnetic field vector, and let's say this one goes up and down sinusoidally in the x direction, and we know from Maxwell's equations the magnetic field vector is perpendicular to it, and that's in blue, and it's propagating out. And if we just do a click, you can see the electromagnetic wave propagating out. Now, polarization is defined as, it's defined relative to the ground or to some other surface, okay? And most often it's defined relative to the ground, okay? When the electric field vector is vertical relative to the ground or perpendicular to the ground, that's called vertical linear polarization. And here we see, this is linear polarization because if we look from the back of where we're transmitting, the electric field vector goes up and down along a line. Just goes up and down along the line. Goes down, down, and up. See if I can do this. It goes down, up, down, up, down, up. Okay? Now, and that's called vertical polarization. And again, with respect to the Earth. Now, why would we use that? Well, it turns out that over water, the backscatter from the sea, which you don't want to see, no pun intended, is less at many frequencies with vertical polarization. So you can help yourself if you don't want to see the background by transmitting at vertical polarization with if you're in a sea-based radar on a ship, say. It also helps out with multipath under conditions. But if you're, say, a radar that's looking upwards at aircraft, and a big part of the scattering of aircraft are the wings, and most of the time they're horizontal, you'd like the electric field to be horizontal. You'd like linear horizontal polarization. Okay? Now you can remember when we talked in the first lecture, and we talked in the lecture on cross-section, that the cross-section and the reflections that we get depend on the orientation of the electric field vector. And if you go back to those simulations, those finite domain simulations of an electromagnetic wave hitting a plate, the properties of the leading edge and the trailing edge diffraction, which caused reflections back to the radar, were different when the electric field vector was oriented differently. That's because of the different polarizations. So if you're back here, just imagine an observer back here at the source of the radiation looking out. You just look at how the electric field vector of the electromagnetic radiation, if it's going up and down, it's linearly vertical. If it's back and forth, it's vertical. Back and forth, it's horizontal. Now, there's another kind of polarization that you can have, where you have the electric field vector, and you can mix together the polarization, and you offset one by 90 degrees in phase, and you end up with circular polarization. And by that I mean the electric field vector, when you add the sum of those two electric fields that we made up. Electromagnetic waves can be made up of superpositions of, you can have two cross dipoles, each emitting out of phase by 90 degrees, And what the electric field that's transmitted will be the sum of the two electric fields. And so the sum electric field that's transmitted will have a sum electric field vector that will rotate in space. Okay, and if the amplitude of each electric field that's transmitted, and the horizontal and the vertical are the same, the electric field will go in a circle. Okay, and it can go in a circle in one direction or the other. And here we have that a visualization of the electric field vector propagating out, sort of like a slinky. The tip of the electric field would follow the path of a slinky. Now, if you're behind the vector, you're at the antenna looking out, and the electric field vector goes in a clockwise direction, it's called right-handed circular polarization. And if the electric field vector goes in the opposite or counterclockwise direction, that's a left-handed circular polarization vector. Well, why would we want to do this? First, let's look at a pretty animation. Animations are always fun. Okay? So this is what, for right-handed circular polarization, the electric field vector would be the electric field vector as a function of time, the total electric field vector. Okay? And that would be for right-handed circular. Now let's look at a left-handed circular polarization. Okay? Okay, now why would one want to do this? Why would one want to do this? There are lots of times when you want to calculate, when targets can have mixed properties. You don't know, like, whether a target that would be preferentially would give off one kind of polarization or another, and so you might want to propagate both linear and horizontal at the same time. Or there are uses that if you in many different radars where you can discriminate one kind of a target, one thing from another, and rain mitigation is probably the best one. Rain, you'll see in the lecture, actually it's the next lecture, lecture 7, where we discuss in detail backscatter of all different kinds of unwanted targets, and one of them is rain. If you have a radar that's operating and it's raining outside, well, you're going to have backscatter from the rain and backscatter from, say, aircraft targets that are of interest. Okay? Now, what is rain? It's spheres. Okay? And the mechanism, as you'll see in the next lecture, of how the rain scatters back is it refracts into the raindrop, and it changes sign. It changes if you transmit circular polarization of, say, right-handed circular polarization, as it reflects in the raindrop, and it comes back with the opposite sense of polarization. So if you set your antenna up to receive the same polarization that you transmitted, then you don't see the rain. You'll mitigate the rain. If the raindrops are spherical, sometimes elliptical. I'll get into that in the next lecture, so maybe. But the point is that you'll mitigate the range significantly if you transmit circular polarization and receive. Now, what what happens with the targets? Most targets are a mix of linear, of scattering that will come back in each polarization, and so you'll get a mix of polarizations from the target, and you'll lose some a little bit, but you lose an awful lot of the rain. And so transmitting with circular polarization and setting up that receive mechanism that I talked about will help you in a rain problem. Won't solve the whole problem. Doppler processing, which is lecture 8, is really the way to solve it. But it's one of the ways that circular polarization is used. Okay, now let's talk about the different field regions. One of the things that we talked about is that Maxwell's equations, these 4 simple, beautiful equations that tie together electromagnetic fields, electric fields, magnetic fields, currents, and charges. And when we have radiation, Maxwell's equations have to be satisfied. Now, having studied Maxwell's equations, I think I've taken 4 or 5 full-year courses that were essentially Maxwell's equations. From just in undergraduate and graduate school, let me tell you, solving Maxwell's equations for very simple things can be easy, and people make a lifetime, a living solving Maxwell's equations. And when you take such complicated, they look theoretically beautiful, but complicated equations, complicated situations that you want to solve, you have to make approximations. And it turns out the solutions get to be real easy when you're very far away from the antenna. And when you want to do things like calculate the pattern of the antenna, the gain and directivity, polarization issues. You want to calculate the radar scattering cross-section. When you want to do all those things, when you're far, far away, when effectively the antenna appears to be like a point source, and what that really means is that the waves which come out from the antenna as spherical, by the time they get to you, those spheres can be very, very superbly approximated as plane waves. Under those conditions, that's called the far field, and this is the algebraic condition when that's true. If the range is greater than twice the antenna size squared divided by the wavelength, then you're in the far field. And this dude Fraunhofer, he did a lot of the calculations. That's the far field region. And most of radar stuff that we worry about is we deal with. All the power is radiated out there, we assume. The radiated field is a plane wave, I said before. When we get in close to the antenna, it's a lot more difficult. Near field equations are difficult. And here again, I haven't had a picture before, but here's an idealized dipole as a simple antenna, dimension D, in the near field region. So the near field region is actually 2 different regions: a radiating near field region called the Fresnel region, which is between these 2 bounds, and when you're less than, when the range to the point in space that's of interest to you is less than 0.62 times the square root of d squared, d cubed over lambda, then you're in the reactor near field region. That's called very close to the antenna. But there are times when you need to do calculations in each of these regions. If you happen to have built an antenna that for one reason or another has grating lobes and you want to calculate the grating lobes nearby, say for electromagnetic health regions, are the fields weak enough so that they're not a bother to human beings or creatures, there are limits that the government sets. Then you need to do near field calculations, and that's a time when these calculations are done. Or if you're doing calculations right near the antenna where you're calculating things like mutual impedance, you're in the reactive near field region sometimes. So you need to do calculations there. They're a lot tougher. But for just about all the stuff we're going to be dealing with, it's called the far field. The reason for this view graph is to pretty much say to you, hey, there are 3 different regions. Most of the stuff we're going to be doing is in the far field. First, let's talk about the near field, the very near field. Now, with the antenna, you know the goal is to get out all of that energy and to make the transition between the waveguide and the free space as lossless as possible. And when we go from the feed to the antenna, there's discontinuity there. And that discontinuity gives rise to a reflection. This gamma, this is a capital Greek letter gamma. It's a reflection coefficient. And if that gamma is 0, then the incident power is perfectly delivered to the antenna. If it's 1, all of the incident radiation is reflected. And here we have an equivalent circuit. We showed you that. There's the loss in the antenna, the radiation that goes out, and the radiation, the reactance, it's stored in the antenna. And what happens is when it's reflected back is some of the energy, if too much of it is reflected back to the antenna, from the antenna to the transmitter, all hell breaks loose because the transmitter can't stand it. You're sending out megawatts or tens of kilowatts of power. You send back 10% of that, and you got real problems. Transmitters will shut down because big pieces of metal expect efficiency, and if they don't get it, they melt. So there's all sorts of safety devices in these transmitters to make sure, high-power transmitters, to make sure this doesn't happen. But it's a very important thing to design the antenna to maximize this power transfer from the transmission line. Now, it can be modeled, the antenna can be modeled as an impedance. And again, just to remind you, the impedance is the ratio of the voltage to the current at the feed point. Okay? Now, sometimes, and I don't have it on this view graph, a measure of how good that match is called the standing wave ratio, VSWR, variable standing wave ratio. And when all of the power goes out, the standing wave ratio is 1. When all the power is reflected, it's infinite. And the input impedance that you have here defines the frequency range over which your antenna can operate its bandwidth. Okay. Now I'd like to move on to reflector antennas in detail. I went over a little bit of this before. I probably stole a little bit of my own thunder. With a parabolic reflector antenna, remember I said if you have the feed at the focus, the path length from the focus where the source is, reflecting off the parabolic surface, and out to the wavefront is the same for all rays of energy coming out. So we have a fine wavefront here. What I'm going to focus on here is the issue of the trade-offs that go on, and how you design where you put the antenna. Well, you have to put the antenna pretty much at the focus. You have a little bit of leeway one way or the other, but how you design this feed. Okay? Because if we make the feed too big, some of the energy will spill over, and we won't efficiently have the energy reflect off the parabola and go out. And if I have the energy focus too narrow, then the effective diameter of my antenna won't be that big. I would like to see uniform illumination of the whole parabola and then none afterwards. And that assumes things you just can't do in a feed very well. You can taper the illumination of the feed. That can help out. But anyway, for a realistic antenna, there are all these different areas, and I'm just going to go over them for a minute. We've got the main lobe at 0 degrees, straight out here on axis. And then this is a little, it doesn't have a minimum before the side lobe, but it's called a vestigial lobe, a shoulder. But when you go down to a null and then up, we call that the first side lobe. And then we see the side lobes get increasingly down lower and lower. And when we have a real, this is a null, not a local minimum, but it's a real null down there. And then we have some radiation out a little after 90 degrees, which spills over. So when the angle is over here, some of the radiation from the feed leaked over here, and it's down in the side lobe region, below the first side lobe. And we can even get energy that leaks and diffracts back around the back. So we can even have some energy, albeit it's down 40 dB, that's 10,000 times down from the peak. But we can have some energy, and that's go all the way around the back, and that's called the back lobe. So the design of the feed is a very important thing. Now, one of the ways that we issues that we can have with the parabolic feed are that you have to take waveguide or cable, and you have to have that feed. When you saw that feed with the parabola, it was sort of hanging there in space, and it just doesn't hang there in space. Let's just go back for a minute. You know, that feed just doesn't hang there in space. You have to have some struts from the antenna holding it up, and they're going to block some of the energy going out, so you're going to have a loss and gain from that. Then you're going to have a feed that's going to take the energy from the transmitter and loop it around behind. And you're going to, if it's a heavy feed, you're going to have structure to hold it. So you're going to have blockage issues. There's another design rather than a simple parabolic antenna that you can use to mitigate some of these problems, and that's called a Cassegrain reflector antenna. If there are any of you out there that deal with telescopes, Cassegrain is one of the optical designs that telescopes are. There's another a Gregorian design, which I won't get into in this lecture at this detail. But anyway, what you do is you have your parabola, and here's where we put the feed if we were going to use a parabolic feed. But if we take and we put a hyperbola, which is another geometric shape, relative to this focal point, we put a hyperbola, then what happens is, and then I put at the focus, at the real focus, I put the feed back here, then what will happen, this is the focus of the hyperbola, then what will happen is the rays coming out from effectively just the back of the parabola's dish will go out and hit this parabolic, what we call a subreflector, and then we'll go back, reflect out again to the dish, and we'll all go out parallel, all with the same path length from the feed, and everything's copacetic. Now, what have we done and what have we gained? We don't have a big structure that's going out and around with the feed, and we have a lot less blockage, so we're able to get better, a more efficient antenna, more gain. Okay, and that's called a Cassegrain feed. One thing I didn't point out is that at very high frequencies, the loss for 100 feet of waveguide at say 3 centimeters can be as much as 7 or 8 dB if you have 100 feet of waveguide, and at say L band, which is 23 centimeters, it can go down to the order of less than a dB per 100 feet of waveguide. So the attenuation that you have in the waveguide can be a significant factor in wanting to choose a Cassegrain feed. Okay? Now, what do these guys look like? Well, Altair is a good example of an antenna that has a Cassegrain feed mode. But this is a dual frequency antenna. It transmits at 2 frequencies. It transmits at UHF with a Cassegrain feed, a feedback here. There's the horn, the Cassegrain horn, which goes out to a subreflector here, and then back to the parabola and out. But back here, it's got another feed for VHF. Well, you say, gee, doesn't this subreflector get in the way? Well, it's made with a frequency selective surface. Think of it as it's a metal plate with holes in it that are designed to let VHF energy through, but to reflect UHF energy. I mean, this is a powerful antenna. Its peak powers in megawatts. So it's a very carefully designed, this frequency selective surface, is not for children to design. There's an art form designing these at high power. consequently. But this particular antenna, 45.7 meters across, 880,000 pounds, 440 tons. It uses both a parabolic and Cassegrain feeds. So it's an interesting example for you to see.